as you may have heard in one of the previous mentions by myself or my BDTI co-founder, Phil Lapsley, BDTI is an engineering services firm. We do product development, engineering services, especially for highly optimized software, for embedded vision and other algorithmic intensive applications on various kinds of specialized parallel processors. We also do a lot of benchmarking and evaluation of processors, tools, and algorithms to help developers choose the best processor, tool, algorithm, or what have you for their product. And lately, we've been having a lot of clients contact us with embedded vision related projects, and I've been really shocked to see just how much confusion there is about processors. I mean, oftentimes our clients are calling us and they're saying, okay, we're going to build this kind of product and we're going to do it on this kind of processor. And that kind of processor is so off from what they should be using for that kind of product. It's really kind of remarkable. And what I've concluded after a number of these conversations is this is such a new area. So many people are tackling vision projects for the first time. And there's so many processors to choose from and new ones popping up every month. It's just very confusing. And we don't have these kind of canonical design patterns that we have in many other fields. Like if I said, you know, I was going to build a low power digital audio widget, we've had so much experience as an industry, we know exactly where to go, exactly what kind of processor we should use for a low power audio thing. But when I'm trying to build an embedded vision thing, there's enormous variety about what an embedded vision thing can be. And there's an enormous variety of processors that can be used. And people haven't figured out the patterns yet. I think neither the vendors nor the developers, the system designers, have figured out what the patterns are. So I'm going to try and take a first cut at mapping out the space, in particular highlighting some of the recent developments that I think are most significant and most important in this landscape of processors for embedded vision. So when it comes time for you to choose your processor, hopefully this will serve as a starting point for a kind of map on how to do that. In my previous presentation on tools, I presented some kind of fundamental trade-offs between things like portability and productivity and efficiency, depending on what kinds of tools and programming paradigms you choose. There are similar fundamental, even I think more vivid fundamental trade-offs with processors. We'd like to have high performance because vision applications generally demand a lot of performance. Of course, we'd like to have really good efficiency, so we get that high performance at low cost, low power, small size. Of course, we want ease of development, maximum productivity for quick time to market. And we also want a lot of flexibility. So if we change our minds about what sort of algorithm we're using, what kind of sensors we're going to use, or what have you, we don't have to start over from scratch. And especially in vision, because it's such an iterative kind of experimental field where people keep trying new types of algorithms, new types of sensors, and so on, you need that flexibility. And of course, you can't maximize all of these things at once. If you choose the most efficient processor, you're going to give something up, usually related to flexibility and ease of development, for example. But how do these trade-offs play out? How can you optimize where you are in the trade-off curve? That's a big part of what I want to talk about today. So what this might look like in one, well, I guess in two dimensions, one trade-off is looking at the trade-off between development effort and what I'd call processing efficiency, performance per dollar or performance per watt. If you live in the lower left-hand portion of this curve, life is really nice because you don't need a huge amount of performance efficiency, and so you get to use the easiest processor for you to use, and your development effort is really low. That's great. Unfortunately, most of us don't get to live there, at least not for very long, because if you're in any kind of competitive market where there's big money to be made, you may think you're living in the lower left-hand quadrant, but then a competitor comes along and puts in more effort and has a better product at a lower cost or longer battery life or what have you. So I think most of the interesting opportunities, unfortunately, don't exist in the lower left. They're more in the center or the upper right. And as you push for more and more performance efficiency, the development effort goes up gradually at first and then much more quickly. And we get into kind of a diminishing returns situation where once we're up on this curve, each additional increment of performance per dollar or performance per watt costs us a lot more in development effort. Now, of course, this is a simplification. This is a very conceptual chart. Real life, actual chips you can buy don't really look exactly like this. Real life is a bit messier. Real life maybe looks more like this. The shape of the curve holds, but it's not single curve with all processor options falling nicely along that curve. And so what this means is it's both kind of a challenge and an opportunity, right? The challenge is harder to understand exactly where you need to be on this curve and what's your best option. But the opportunity is you may be able to cheat the curve, so to speak. You may be able to find that one processor that's a bit further up and to the left than the other options. Get more, in other words, get you more processing efficiency at a given level of development effort, or the same processing efficiency for less development effort than other processors that are in a similar kind of zone. And of course, exactly where processors fall in this trade-off space, individual processors fall, depends entirely on the details of your application. This isn't like a global curve for all applications. It's going to be, in fact, a different curve for each application. But the shape of the curve, I think, generally holds true. Now, of course, what happens over time is the whole curve moves up. A rising tide raises all boats. Silicon fabrication process improvements enable chips to do more per unit silicon, per joule of energy. And architecture improvements, similarly, enable us to get more useful work done per cost or per power. And of course, the whole curve doesn't move up all at once. Not, all processors don't come out with a new successor generation on January 1st each year and take a uniform, step up in terms of processing efficiency or improvement in development effort. It moves in an irregular, uneven fits and starts. And so a particular processor may, for a period of time, for a particular application, be significantly ahead. It may have moved the curve up, so to speak, before its peers, its competitors have. And this brings me to the concept of heterogeneous processing, which you've, I think, heard a lot about today. In fact, maybe it's the single most common thread that's run through most of the presentations, many if not most of the presentations today. A way to think about heterogeneous processing in this context of this kind of trade-off is it's another way to sort of cheat the curve by trying to combine the best of two worlds, taking two processor types, putting them ideally on the same chip or at least in the same system, where one processor type is much more efficient but harder to use. And so you put your heavy lifting portions of your application on that processor type and you suffer the additional development effort, but hopefully most of your code runs on the other processor type. Usually that's the CPU. So this might be CPU plus GPU, for example, or CPU plus DSP, or CPU plus whatever, fill in the blanks. So the idea is the 20% of your code that takes 80% of the cycles, you pay the price, extra development effort for that minority of the code to get the better efficiency, but the 80% of the code that consumes the 20% of the processor cycles, you keep that on the CPU and get the benefit of ease of development. Now, of course, again, this is an oversimplification because even the mere act of dividing the application up between different kinds of processing engines or even multiple instances of the same kind of processing engine, that introduces additional complexity into your development process, which isn't really accounted for by this simplified graphic that shows literally sort of taking the best of both worlds. Nevertheless, I think this is a valid way to think about what you can get if you thoughtfully employ heterogeneous processing, and it helps explain why almost everyone who's doing embedded vision is employing heterogeneous processing today. So that's a key trend, and the first trend I really want to highlight in terms of what's happening in processors is heterogeneous processing has become virtually universal for embedded vision. And a great example of this, and another trend in and of itself, is mobile application processors. These are the processors that power our smartphones and tablets, and they are poster children for heterogeneous processing. They have many, many processor cores of many different types. Of course, there's usually a multi-core CPU There's then GPU, which are getting increasingly powerful. There are often DSPs, there are ISPs, image signal processors, for improving the image coming in from the image sensor. There may be specialized video compression engines, and the list goes on and on. So even though these are very small, relatively low-cost chips, they have an incredible diversity of processing elements, and hence they're really great examples of heterogeneous processing. Now, another key thing about mobile application processors is that they are produced in incredible volumes, right? Because mobile phones and tablets are produced in incredible volumes on the order of, 1 billion units a year collectively. And what that means is there's a vast, vast investment in improving these processors architecturally, from a silicon fabrication perspective, from an enabling software and tools and libraries perspective. And if you can leverage that, that can be a big win. Now, of course, if your product is being deployed on a mobile device, if you're making a mobile app, then you're taking advantage of the capabilities and the investment, the collective industry investment in these mobile application processors. But what if you're not? What if you're not writing a mobile app, you're building a purpose-built system? Well, some purpose-built systems these days are actually being made out of tablets and smartphones. For example, if you go into the specialties chain of sandwich shops in the Bay Area, their self-serve order kiosks are simply iPads that are bolted down to a counter and that run their order entry software. So it's literally a consumer tablet simply repurposed for an application that in previous generations would have been a specialized, purpose-built embedded system. In other cases, people are taking the guts of a tablet or smartphone and packaging it into a different kind of form factor, into a different kind of system. The challenge there is that because the mobile application processors are designed for smartphones and tablets, which are huge, huge high volume markets, in general, the vendors don't want to talk to you and don't want to sell you parts unless you're ready to sign up to buy tens of millions of units a year. A way around this is that some of the vendors are offering what they call system on modules, SOMs, where you can buy from a partner, a supplier of theirs, a little module that has the application processor, the DRAM, and a few other key components, and then you can build a motherboard, essentially, a carrier board that SOM plugs into. It lets you build your custom purpose-built system, leveraging the mobile application processor and all of its incredible capabilities, as well as its software development infrastructure, which is quite sophisticated. Now, a catch there regarding the software development infrastructure, though, is that you may not be able to get access to that software development infrastructure. Right? If you go to Samsung or Qualcomm and say, "Hey, I'm going to buy these SOMs, 1,000 units, 10,000 units, whatever, 100,000 units," you're not going to get, of course, the same kind of support as if you're Samsung signing up to buy 10 million units a month for a mobile phone. So a key question is, of all that great infrastructure that's being provided for software development, especially to enable using the heterogeneous processing aspects of these chips, what can you actually get access to? Mobile application processors are incredibly powerful, but can you buy them physically? Can you get a hold of them? And can you get access to the software development infrastructure? The OS ports and board support packages, the APIs, the documentation, the specialized tools to enable using the heterogeneous processing elements? Not necessarily. And so that's a complication here, and it means you have to look at it on a case-by-case basis with each individual processor supplier. The next trend that I think is really a huge one for embedded vision, and we've also heard quite a bit about, including in Harris's presentation immediately preceding this, is the GPU, general purpose GPU trend. The idea of using GPUs to do things other than graphics. That's, of course, not a new idea, but it's relatively new in the mobile and embedded space. It's been used for a while in PCs and in high-performance computing, server farms, supercomputing applications. But in mobile and embedded devices, it's relatively new. We're just seeing the emergence of things like OpenCL to enable harnessing GPU compute in mobile devices. This is, I think, really important because the GPUs are going to be there regardless in these, especially in these mobile application processors. They're going to want to provide good 3D graphics. It's not a question of will there be a GPU or not. There's going to be a GPU, just like there's going to be a CPU. The question is, what can we do with the GPU, especially in an application where we don't need it for sophisticated 3D graphics? Can we repurpose it to do our data parallel, especially the kind of front end, filtering and rectification and edge detection kinds of algorithms that tend to be highly data parallel? And the answer is now changing from not really or only for the hardcore, really dedicated people who want to get into all the details to, yeah, actually you can, because here's our OpenCL implementation for our mobile application processor. So that, I think, is a real plus. Another trend that I think is significant is we've seen the emergence of processors designed specifically for vision applications and an acceleration of that trend in the last year or so. I think as the industry has started to realize that there are big volume opportunities here in things like gesture control for consumer electronics and automotive safety systems, and that there is this challenge of needing to deliver a lot of performance for not a lot of cost and power, and wanting to sort of cheat these curves and get better, get a better trade-off of performance versus ease of use, for example. Well, one way to do that is to provide a more specialized architecture that's more tuned to the application. That's challenging in vision because in vision, the algorithms are, excuse me, are extremely diverse. Even if you narrow it down to a particular application area like automotive safety, the algorithms are still incredibly diverse, in part because the sensors are very diverse. If you look at Mercedes versus Subaru versus Mini, et cetera, and the approaches that they're taking with their automotive safety systems, they're very diverse. Some are using stereo vision, some are using mono vision plus radar, LiDAR, all different kinds of sensors. And of course, different kinds of sensors imply different kinds of algorithms. So this makes it a challenge to build a specialized architecture, given that there's such a diversity of algorithms. Nevertheless, people are doing it. I think they're making some headway. Most of these vision-oriented processors are actually not sold as chips. They're sold as silicon intellectual property cores, the ARM business model, to be integrated into a chip by a chip supplier. For example, there was just an announcement this week by Freescale that they're incorporating a vision-specific processor, coprocessor core from CogniView into their chips for automotive safety, for vision-based automotive safety applications. And I think we will see more and more of this. The Google Project Tango that you may have read about recently, where Google's distributing prototype smartphones and now tablets with 3D sensing in it, that's powered by a vision-specific coprocessor chip by a company called Movidius. So most of the vision-specific processors that we see being offered by companies like CogniView, Siva, Cadence, Vidiantis, and Apical, these are licensable silicon IP intended to be integrated into a chip. But there are a few that are sold as chips. We heard in the other session earlier this afternoon from Analog Devices. They have their own PVP, pipeline vision processor, their vision coprocessor they've integrated into their own Blackfin chips. Mobileye is a dominant company in the automotive safety space. They make chips with their own proprietary vision coprocessor. Movidius, likewise. Texas Instruments, likewise, with their EVE vision coprocessor. There are also some vendors that offer a do-it-yourself approach, giving chip designers the ability, or system designers the ability to craft their own vision processor. Synopsys does this for IC designers. Synopsys has tools to enable IC designers to craft their own vision processor, which can be appealing given that diversity. If you know what you're doing, what kinds of sensors, what kind of data types, what types of algorithms, then you can craft your own processor and cheat the curve that way, get a better trade-off between performance efficiency and ease of use than if you use somebody else's processor that somebody else designed. We can also do this with FPGAs, and the Xilinx Zinc product is a great example of this, where it couples an ARM CPU on the same chip with FPGA fabric, and the FPGA fabric can be used to form custom coprocessors that are tailored to the exact needs of your application, the exact mathematical operations, the exact data types, and so on. It's enabling you to essentially roll your own vision coprocessor. Of course, the challenge here is if you've got a unique processor, you've got a unique programming model, and typically not the same kind of rich infrastructure of libraries and tools and APIs that are available for more mainstream established processor types. OpenVX, as Neil Trevitt presented earlier in this session, could be an equalizer here, right? If these specialized processors support OpenVX, that can add, really enhance ease of development and portability for these specialized vision coprocessors. So what have we learned from our work looking at evaluating, benchmarking, and developing on processors for embedded vision? Well, it's complicated. There are many diverse applications and algorithms, and there are many diverse processors with their unique strengths and weaknesses, programming models, tool chain. Finding the match there is challenging, and my sense is there's a lot of confusion, both by users who are trying to choose processors and also, in many cases, by the suppliers who aren't really sure, well, we have this processor, it has this particular unique set of strengths and weaknesses. We know it's good for certain vision things, but in the universe of vision things, we're not really sure which ones it's best for. And I think it's going to take a little while for that to settle out. And in the meantime, it's a challenge. It's a challenge for developers to figure out which processor they should really use, and for suppliers to figure out which applications and which markets they should be focusing on. It's a complex problem. It's a multi-dimensional optimization problem, right? When I showed those curves, I was simplifying it to 2 dimensions, but there are similar curves for many other aspects of attributes of processor selection. For example, the supply risk associated with, do I go with a relatively new startup company that's untested, where there may be higher risk? It looks like a better product, but there's higher risk in terms of their ability to deliver. So there are many of those trade-offs that have to be evaluated, and the bottom line for me is, you want to allocate some time. This isn't a decision you want to make in a few weeks. You want to give it some time, really understand what your application requirements are, really dig in and understand the processor strengths and weaknesses so you can make a well-informed decision. The good news here is the collective investment of the industry in building processors for vision and all of the associated application development infrastructure has become really substantial and is growing. And so I think we can expect to see return on that investment in the form of more options, more processor options, better processor options improving faster, not just the silicon, but also the associated tools, APIs, and so on. And that's, I think, great news for product developers. And part of why that's happening is a specific focus on vision. Part of why it's happening is kind of riding the coattails of related markets like mobile application processors, which today are not specifically being designed for vision, but are being designed for related kinds of capabilities. And kind of as a side effect of that, huge investment is going into delivering very, very powerful processors that are very energy efficient, very cost efficient for vision applications, and have really rich application development infrastructure. And regarding application development infrastructure, of course, a processor is only as good as its tools, its documentation, its technical support, and so on. That's obviously one of the dimensions that goes into selecting a processor, and it's one of the dimensions that can be more difficult to evaluate before you've gotten waist deep into your own product development. My wish list is, well, I'd like to see more processors optimized for vision. I think also more attention is needed to flexible I/O options. FPGAs have always been very good at this, and that's a particular strength of FPGAs. Whatever you want to plug into the FPGA, generally speaking, you can find a way to plug it in. But for most other kinds of chips used in embedded systems, they have relatively fixed I/O options. And that can be a challenge because the sensors are evolving just as fast as the processors and the sensor interfaces. So we may start a product development thinking we're using a certain kind of sensor, and then realize 6 months in we actually have to use a different kind of sensor, or maybe multiple sensors. And if the interface isn't there, that can be a real problem. Also, of course, we want the processors to be readily available. Some of these mobile application processors are awesome, except you can't get them. Obviously, you have to be able to get them, not only the processors, but all the supporting infrastructure to be able to effectively use them. We'd like these processors to be easier to program, and the good news is some real improvements are being made there through many initiatives that we've heard about here today, like OpenVX, like OpenCL, OpenCV, HSA, and so on. And then there's also the roadmap risk aspect. Typically when we design a product, we're not thinking just about that product, but we're also thinking about a series of successor products. We're going to make a big investment in learning how to use that processor and its tools. porting our code, optimizing our code. We hope to be able to reuse that over multiple generations of our product. To have confidence that we can do that, we have to have confidence in our processor vendor's roadmap. And that's harder to do right now in vision than it is in other more mature fields, because there's a lot of just chaos happening now with companies entering the market, companies adjusting their strategies and their market focuses as they figure out where they think they have the best opportunities. So that's what I have for you today. I think I have time for maybe 2 or 3 questions, and I've given you here some pointers to resources on the Embedded Vision Alliance website where you can dig in more depth if you're interested.